Hi everyone, and welcome back to another AP Calculus video. Today we're going to talk about an application of separation of variables, and we're going to review a concept that you probably learned back in your early algebra days, and we're going to see where a formula that we've used came from, and it came from calculus and using separation of variables to solve. So there's an episode of Star Trek that's one of my favorites, and it's called The Trouble with Tribbles. And I guess it's not necessarily one of my favorites, but it's one of the more popular ones. And I distinctly remember in 9th grade English class having to read the script for The Trouble with Tribbles. And so I know the episode very well. And in this episode, they come across kind of this little alien species called a tribble. And they're charged with taking care of it. And for whatever reason, it comes onto the Enterprise. And what they don't understand and realize is that this has an exponential growth rate. These tribbles multiply exponentially. And every so many hours, and I'm not sure, what the periods are, but after so many hours, they've, multiplied by a certain amount. And so let's just suppose that we have a variety of tribble. And it's on the Enterprise, and Lieutenant Spock estimates that these tribbles produce 10 more tribbles, that each single tribble will produce 10 more tribbles every 12 hours. That seems to be the rate at which they're growing. If we allow t to be the number of 12-hour periods and y to represent the number of tribbles, then we can model the situation using a differential equation. dy dt, which is the rate of change of the tribbles over time, is 10y. So however many tribbles there are, each one will produce 10. So if we have 2 tribbles, then we have this equation where our rate is dy dt is 20. Now we get this differential equation. It's called the law of exponential change, and basically it says y is changing at a rate proportional to the amount present. So each tribble creates 10 more every period of time. Then we're taking 10, that's our constant, multiplying it by the population. So the rate of change is proportional to the number present. So if we had 10 tribbles, then our rate of change would be higher. So we do not have a constant rate of change, but rather a rate of change that's changing as our population increases or decreases. So this model also assumes a continuous growth rate. And what that means is that within a 12-hour period, it's not what we call a discrete amount of time that it takes for these tribbles to multiply. You have tribbles at various stages of their life. They grow at different rates. And so what's happening is within that 12-hour period, you have tribbles that are multiplying and creating more tribbles. We also need to understand that in reality, this 10 tribbles per tribble every 12 hours really is just an estimate based on what the trends are that Spock sees using real-world data. So within that 12-hour period, you could have some tribbles being born in the beginning of the 12-hour period and some being born at the end of the 12-hour period and some in the middle. And so the idea is that if you break down your time into discrete intervals, when you count it, here's how we're counting it. We're counting them as 12-hour periods. So we have a continuous rate of growth here rather than a discrete rate of growth. Discrete would be at the end of 12 hours, every tribble present would create 10 more. And it would only happen at the 12-hour mark. So that's what we mean by discrete versus continuous. So let's find a particular solution for this differential equation. And we're going to assume that at t equals 0, we started with 2 tribbles, right? So dy dt equals 10y. We're going to separate our variables. We're going to divide the y over. We're going to have 1 over y dy equals 10 dt. So when I go ahead and integrate all of this, I get the natural log of the absolute value of y equals 10t and then plus c. Well, taking into account what we talked about in our first video about separation of variables, we know that we need to raise each side as a power of e and then eventually drop those absolute value bars before we can solve for that constant. So let's go ahead and do that. If I raise both sides as a power of e, and then kind of rewrite things, I'm going to kind of skip a few steps here. I'm going to have e to the c times e to the 10t. And then when I drop these bars, I get plus or minus e to the c, e to the 10t. And if I know at t equals 0, there's 2 tribbles, that means my population was 2. And then e to the 0, that's just 1. that means that 2 is going to be that plus or minus e to the c. So that's that constant that's in front. And we end with this solution. We get y equals 2 times e to the 10t. Now, you might be thinking to yourself, hey, this looks familiar, and maybe you are. And let's see if we can find some identification here with the numbers in our final result and what we were given. Now, at t equals 0, our population was 2. Well, anytime t is 0, e to the 10t or e to the whatever t is always going to turn into 1. So that will always happen, which means that if we know our starting value for any situation, not just the triple situation, that starting value will be right here. So this is our starting value. Now we're going to start referring to this as y naught. That means the value of y at the beginning of time when t was 0. This 10 should also be familiar. And if we look at our work throughout, the 10 was that rate of change. And nowhere is there any indication that through this process of separation of variables will the 10 be touched ever. And so this is always my rate. So we end up with this. If we call the rate r, or in I know in many textbooks we could also call it our constant k. It's the constant of proportionality, right? We said that when the growth rate is proportional to the number present, in other words, you can write it as, hey, dy dt equals 10y. We can refer to this as our constant of proportionality k. Sometimes we refer to it as a rate also. But essentially we end with this equation. Y equals y naught times e to the k t. So anytime we have a situation where we're going to have proportional growth, a rate of growth, dy dt equals k times y, we can jump straight to this equation. We don't have to do the separation of variables because it'll always be that if I am given an information like this, I can always end like this. Now, if you forget that, you always have separation of variables to fall back on. But what I want you to take away from here is that we can skip all that work and just jump straight from, hey, if I know k is 10, that goes right here, e to the 10t, and then whatever my beginning value is, if I'm told t equals 0, I'm going to use that in the problem, and I'm going to use 2 as my initial population. It's my starting value. Now, we also see this equation in a specific application in algebra class involving what we call continuous growth or continuously compounded interest. And it is just one application of this, and it is we call it our Pert equation. So let's review that from algebra. So if dy dt equals k times y, so some constant times the population. So in other words, if my population is doubling, it would be 2 times y. If my population is producing 10 more triples per triple, 10y. If my money in my account is growing by, it's tripling every time period, then it's 3y. If you can write it as, hey, I'm going to take whatever money I have or whatever beginning amount I have and multiply it by something, then you can write a differential equation, dy dt equals k times y. So if we can write it like that, then we have this solution that will always look like this. So we're skipping all the integration that happens in the middle. Now, if we have money, oftentimes we refer to this equation as Pert, where instead of y naught, we use p. And instead of k, we use r. R is our percentage rate, it's our interest rate. So anytime we have a situation here where it's not dealing with money, or maybe it is dealing with money, who knows, but if you have a value there, e to the something t, if that r or that k value is positive, then we know whatever our amount is growing. Our triple value is growing, our money in our bank account is growing. If it's negative, it means we're decaying. It means we're decreasing in our amounts. So let's take a look at some applications here. So money problems, right? We've all got them. So anytime we're talking about continuously compounded interest, so what this means is we're taking our interest, we're taking our bank account, and we're saying, hey, my new amount in my bank, or the rate of change in my bank, is I'm adding a certain percentage. So if my interest rate is like 5%, then I'm adding 0.05 times whatever amount is in that account. So it ends up looking like this, where dy dt equals 0.05 times y. That's my rate of change. So that's what I'm doing. That's what I'm increasing my bank account by. So when I take this amount here, when I'm trying to find my new amount, whether it's tribbles or whether it's money in my account, what I'm trying to do is I'm taking this and I want to be able to use this equation and jump right to this equation and avoid all that middle work so I can save some time on my exam. Now, we also have another equation that is quite common, and just for the sake of being thorough, we'll review this, but this is what we would call discretely compounded interest. So in a continuous situation, even between the beginning and the end of the time period, money is being added on, interest is being accrued. In discretely compounded interest, what happens is the bank will wait until the end of the month to add the interest on. So any money that you've had in there is not earning interest until the end of the month. So you could have put $100 in on January 1st, in the middle deposited 10 grand here or there, and then on January 30th removed most of your money so that you're at the end with $100. And in a discretely compounded interest model, they would only give you interest on what's there at the end of the month. So we can compound that interest, within our time period. So maybe within the month we want to compound it weekly. Well, there are equations for that, and then that would be at the end of the week, they would calculate your interest and add that on. But if you put $1 million in on Tuesday and took it out on Wednesday, that would not be included, because in a discretely compounded interest model, you would only take what's there at the end of the time period. Most models are what we call continuously compounded interest. So if you put $1 million in there and let it sit for a day, it'll earn fractions of pennies in interest for you before you take it out the next day. So that's what most of the banking industry uses, is a continuous compound interest. And credit cards will do the same thing, in that you have to kind of pay attention to the difference between your interest rates. They'll give you a couple different ones, and that's another lesson for another day. But this is the equation for discretely compounded interest, where if the time period is measured like in a year, and we're compounding weekly, then N would represent within the one time period how many times are you going to compound. Weekly would be 52 weeks in a year. Monthly would be 12 months in a year. So if we were going to take our tribble example, we would figure out, if we wanted to figure out a better example of what's happening, we would take the 12 hours and maybe we compound it every hour. So N would be 12 if T were to represent a 12-hour period, if that makes sense. So T is the big time period, N is the number of times that you would compound within that time period. And just as a quick little aside, and maybe this is a good video for another day, if you take this value here, this 1 plus R over N to the NT, it looks a lot like this, 1 plus 1 over N to the N. And the limit, as N approaches infinity, of this value is actually E. That's where we get that natural number E from. And so it's no coincidence here that they look similar. And if you were to be creative about some algebra here, you could turn this discretely compounded interest model into a limit and get it to equal the continuous model. So moving on, let's just do a little bit of an example here where we have to use our equations from above. So complete the table for the investment if interest is compounded continuously. So let's take a look. Remember, continuous, we like that Pert equation. So we can write it in a number of ways, right? E to the RT, or E to the RT. Oftentimes we'll say A, where A is your beginning amount, P is your principal, that's what you start with, and then R is your percentage. So this is R, this is your principal amount, and then it tells you some other information. So let's fill out the first one here, and we'll get our graphing calculator out and we'll use that, but let's do a little bit of setup here. So for the first one, we'll highlight it here in yellow. My new amount A, or you can use Y, would be 100, that's my initial deposit, times E. Now I'm going to change this to 0.023. Always change any percentage rates to decimals. 0.023, and then we're going to multiply it by the time. So let's do our amount in 30 years. Okay, so T is 30. So we're going to plug that into our graph, into our calculator, and work it out. Now when I work it out and plug it in, we get $199. So not that great. So now let's take a look at what happens when we're trying to find the doubling time. So to solve for and I get that my doubling time is the natural log of 2 divided by 0.023. Now that's my exact value. I can also pull up my calculator and get the estimate for the years. There we go. Whoops. Put out of that. Natural log of 2, put parentheses around everything, divided by 0.023, and boom, about 30.147 years. Now here it's okay to round to 2 places if we're dealing with money, like I did up here, but in our doubling time, I'm going to go ahead and round to 3 places like I'm supposed to here in AP Calculus. Now, the next type of problem asks me to complete the table for an investment of $500, and if that investment is $500, we need to find what the rate was when I started with $500 and it took 12 years to double. So I'm going to approach this problem by just starting with the setup. So I'm going to say A equals, so we had 500, and then e to the RT. Now, if it took 12 years to double, that's giving me enough information to figure out what my interest rate was. Because I know that I had $1,000 at the end of a 12-year period. So I'm going to solve for R in the same way that I solved for T in the previous problem. So I'm going to divide both sides by 500. And then I'm going to take the natural log. And when I do, it's going to cancel the e away. When I do natural log of both sides, I get 12R. So the natural log of 2 divided by 12 gives me the rate. So whatever that decimal value is, that's the answer that I'll be putting in my box. So I get about 0.05776, which I'll round to 3 places here at truncate. 5.776% is my annual rate with the given information. And then the last thing I'll do is I'll find the amount after 30 years. And that's an easy enough thing to do with my calculator. I don't think I even need to write it down, but just remember on an AP exam, you definitely want to write down what you put in a calculator. And it would look a little something like this. So I would do 500, that's my initial deposit, times E. And then I would take my decimal, change it back to a decimal, my rate here, and then times 30, because we want the amount in 30 years. We'd have about 28, 28, 23. 28, 28, 23, so $2,828. So that's how we use those equations, in particular the continuous one. I'm not going to worry too much about the compound interest that's discrete. The trick here is just you plug it in and you'll still work it the same way that you would with a continuous problem, but you'd have an n where you'd figure out, if you're compounding monthly or whatever. You'd still plug things in a similar fashion. So let's move on and let's talk a little bit about some other applications that we're going to see throughout our problems. So when we talk about the half-life of a material, we're talking about the time it takes for it to decay by exactly 1/2 of what it started at. And when we talk about an exponential growth or decay situation, exponential decay, when we talk about this half-life, the nice thing is it doesn't matter what we start with, it'll always take the same amount of time to decrease by half the amount. So the half-life of a certain radioactive substance is the amount of time it takes for the substance to reduce by half. Suppose a sample of cerium-142 loses 99% of its radioactive matter in 199 hours. So that's not the half-life. It takes 199 hours to reduce by 99%, which means you're left with 1%, right? What is the half-life? So we are going to use this equation, and we know that y equals the beginning amount, e to the r, or kt. Okay, so we know that if we start with 100%, so let's let y naught be 1 for 100%, and let's let y be 0.01. So that's the 1% that's left. So if it lost 99%, 1% is left. So how much time does it take? Well, 199 hours. So we need to know the rate at which it's decaying. We have to solve for that before we can even think of finding the half-life. All right, so here we go. I'm going to natural log both sides. So I get 199k. Oh, and when I divide by 199, that's going to be my answer. So k is approximately negative 0.02314. I'm going to keep that on my computer screen because I'm going to use that here in a minute, because now I'm ready to find the half-life. So I know that this is the rate of decay. So now I'm going to figure out, okay, well, it took 199 hours to decrease by 99%. Well, now I just want to decrease by 50%. How long is it going to take to do that? And that number is my half-life. So let's plug everything in. So I'm going to go back to using my y equals. So this time I'm going to let y naught be 1, and this time y is going to be 1/2, because it's going to decrease by half. So I should have this equation 1/2 equals e, and I'm going to use my k value, negative 0.023141 t. And now I'm solving for t. So it's the exact same setup, but I'm solving for t instead of k or r, whatever you want to call it. So I'm still going to natural log both sides. Natural log of 1/2 equals, the natural log and the e are going to go away, so I'll get negative 0.023141 t. And when I divide by that k value, and this is where in my calculator you're going to see that I took that value and I chose it on my screen and divided by the exact value, and that's the way to go. But if you don't have that on the AP exam, it's totally fine just to write it out like this. Just to make sure that you go to, a couple extra places. And that is t. And when you plug it in, you get about 29.952 years. That's my half-life. That's the amount of, or not years, I guess it would be hours. Let's be consistent, right? Hours. Almost missed that. Make sure your units agree, right? We're measuring our time in hours. So about 30 hours is what it takes for it to cut in half. So that's what we call the half-life of this particular substance. So let's take a look at a couple more examples here. These are some tougher examples that you might see. So here we have a situation where we've got electricity draining from a capacitor at a rate proportional to the voltage V across its terminals. And that if t is measured in seconds, then we have this equation. We want to solve the differential equation for V using V sub 0 to denote the value of V when t is 0. Okay, so looking a little bit closer at this, if we want to solve for this differential equation, we're going to have to use our separation of variables. But do we? Couldn't we just realize that what's happening here is that this is k, and this is one of those exponential growth problems. So anytime we're given something of this form, where it's a number times v. So, and I'm going to notice here a couple things. dv dt, that's the variable that's got to be there. So if that's not the variable that's there, then you have to go through the separation of variables. And one particular free response question from a previous AP exam comes to mind where it tries to trick you into making this jump into the Pert equation that we're talking about using here. and you try to make that jump and you get it wrong. And I do believe it's on a BC for your response. So you have to make sure that these two variables are the same. And now we can just kind of jump into this v equals v naught times e to the kt. So instead of the letter y, we're using v. So plugging everything in, solve the differential equations for v to denote the value. Okay, so we don't have any sort of initial condition, but I know that v equals v naught. And I'm just going to put negative 1 over 40 in for k. There's my equation. Boom. Now, if I use separation of variables, it would have taken a lot longer. I would have had to go dv dt equals negative 140v, 1 over 40v. I would have gotten 1 over v dv equals negative 1 over 40 dt. I would have integrated. I would have had the natural log of v. It would have taken a lot longer. I can recognize and just jump right to this Pert equation, y equals y naught e to the kt, and just plop k right in there. Boom, I can save myself a world of hurt and a lot of trouble. So now that we have this equation, v equals v naught e to the negative 1 over 40 t, how long will it take? So what is the time that it takes for the voltage to drop to 10% of its original value? So if we let v naught be 100% or 1, then we're saying how long until v gets to 0.10. I'm going to plug that in. 0.10 equals 1, that's v naught, and then e to the negative 1 over 40t. I'm going to natural log both sides. Divide by negative 1 over 40. And when I punch it into my calculator, that's my precise time. So I get about 92.103, or about a minute and a half, right? So t is measured in seconds as stated above. Be careful when you plug things into your calculator, by the way. Make sure you put parentheses around everything and anything so that your answers will match the correct answers. So let's keep going. Let's see some more examples here. So here we've got the mean life of radioactive nuclei. Ooh, this sounds fun. So let's see. We'll zoom in a little bit so we can read it a little bit better here. Physicists using the radioactive decay equation, okay, so this is our equation, call the number 1 over k the mean life of a radioactive nucleus. The mean life of radon-222 is about 1 over 0.18, so it's telling me that k is 0.18 here, or about 5.6 days. The mean life of a carbon-14 nucleus is more than 8,000 years. Show that 95% of the radioactive nuclei are originally present, and any sample will disintegrate within 3 mean lifetimes. In other words, by the time t is 3 over k. Thus, the mean life of a nucleus gives a quick way to estimate how long the radioactivity of a sample will last. So let's say you're like, Russian scientist in Chernobyl. This is important for you because you want to make sure that 95% or even more of the radioactivity from that big Chernobyl explosion from years and years and years ago has decayed. Same thing, you've got these problems with 3 Mile Island, those sorts of things. This is real life, you guys. This is the sort of thing that people are concerned with. So let's take a look, and we're going to use this equation here, okay? And we're going to show that 95% will decay. So I'm going to go ahead and just kind of start with this, and I'm going to say, well, if I let y equal 0.95, then y naught was 1. So 0.95 equals 1 times e to the negative kt, right? So my goal is to solve for t and to get it looking like what's happening here. So I'm going to go ahead and solve both sides. I'm going to say natural log of 0.95 equals e to the negative kt, natural log of that, cancels away, negative kt, ln of 0.95. So t will equal natural log of 0.95 over negative k. All right, so I'm going to back up here because I accidentally was thinking the wrong way, and maybe you were like me. Really, 95% goes away, so y needs to be 0.05. So I'm going to real quick make a little adjustment here, and maybe you caught this in the beginning. There we go. This is better. This is going to work. Now, the natural log of 0.05 is approximately negative 3. So you get negative 2.99573 over negative k. Well, negative over negative turns to a positive, so it's approximately 3 over k. So we've just proven that, yes, the time it takes for any nucleus here to decay by 95% is 3 over k. And you can see that even the teacher makes some mistakes, but you know, mistakes help us learn, mistakes teach us what we're going to look for, and mistakes make us better in the end. So hopefully this was a helpful video for you. Some of the problems are just a little tricky, and the key here is remembering you can always do separation of variables when you have any sort of, you know, dy dt equals k times y. Remember, when you have this situation here, you can always just jump to y equals y naught e to the kt. The k's are the same. Now, one fair warning, though, is that you need to be really careful because sometimes you'll be given information that says dy dt equals 5x. You need to be careful because that is something different. If these two variables, dy and y, don't agree, then you can't make this jump. You can always do the separation of variables. That goes in the middle, but that will waste a lot of time. So try to recognize and make the jump and save yourself a headache and a hassle. And yeah, the more of these you do, the better you're going to get. The more practice you get, the more confident you're going to feel. So keep at it. Don't ever give up. You've got this.